Hello physics students, this is Dr. Brenzy, and this is the third in a series of videos about Newton's second law and using that law to find missing forces or acceleration. In this video we're going to deal with a problem that involves a ball suspended in the air by two chains. And we have a chain that is suspending the ball at a 60-degree angle, according to this diagram, and a second chain that suspends it from a vertical, from a vertical wall over here to the left. And we're being asked to find the tension in each chain. Before we get started, let's review our process that we use for solving problems involving Newton's second law. So the first thing I want to do is to draw a sketch. The second step, draw a free body diagram. Third step, we want to place the positive y-axis along the normal force. The fourth step, we want to break down forces into their components. The fifth step we want to do is we want to write F net equals ma, Newton's second law, for both of the directions. And then finally we're going to get a system of equations that we want to solve. So that's our six-step process for solving problems involving Newton's second law. A sketch has already been given to me, so in a sense I have a lot of the work done for step one done for me, but it's still useful even on that sketch to fill in any missing information from the text. So I'm going to read the problem. And it says a 50-kilogram ball is suspended in air by two chains as shown below. Find the tension in each chain. Now, as I read through this a second time, I'm going to write down the important information in my sketch. Well, first of all, right away, I notice that we are dealing with a 50-kilogram ball. So let's write 50 kilograms next to that ball. And it says is suspended in air by two chains as shown below. Now the fact that I have two chains means I have two tension forces, so I better be able to figure out which chain is which. So I'm going to call this left-hand chain, that's going to be chain A, and the right-hand chain is going to be chain B. Okay, with that sketch drawn, let's draw a free body diagram. So let's include the sketch. You don't need to do this in your notes, of course. I have to figure out what the ball is interacting with. So I know, first of all, that it interacts with Earth. And it's going to act with chain A. And it's interacting with chain B. I don't have any normal forces in this problem because the ball is not leaning against the surface itself. So what sort of forces are we dealing with? Well, we're dealing with gravitational force when it comes to the interaction with Earth. Chain A is going to give it a tension force. So I'm going to label that as FTA, tension force from chain A. And then the other chain, its tension force is going to be FTB. Okay, these are the three forces, and only these three forces should go in my free body diagram. So let's draw a dot to represent the ball. And let's draw gravitational force. We know that points in a downward direction. We know that the tension force in chain A is going to go along the direction of the chain. So we know that that is pulling the ball toward the left. And then finally chain B is going to pull the ball along this line right here. Now it would be really nice to actually know. Well, actually, let me back up. It does show me that this is a 60-degree angle with the ceiling here. But it would be really nice to know what this angle is right in here. Because when I go on to step 4, I have to break this down into x and y components. Well, If you notice, we have two parallel lines. They are cut by a transversal, and if you remember back to your IAG classes, you'll notice that alternate interior angles are congruent. So if this is 60 degrees, and the measure of this angle also is 60 degrees. Okay, now that I know that, I'm going to actually go ahead and erase this part up here just to make the diagram a little clearer for everybody. Okay, so I have my free body diagram. And now I have to place the positive y-axis along the normal force, but the problem is I don't have any normal force in this problem. Well, if that's the case, then probably the second best thing to do is to make gravity in the negative y direction, because that's what we're used to doing. So let's put gravity in the negative y direction. That means positive y is pointing the opposite direction of that. And on a normal graph, if positive y is pointing up, then positive x is pointing to the right, and negative x is pointing to the left. So now we have drawn our coordinate axes. We know which way is x and which way is y. Our fourth step is to break down any vectors into x and y components. As I look at these vectors here in my free body diagram, I notice that this vector, the tension force from chain A, is already pointing along one of the axes, so that's okay. Likewise, gravity is pointing along one of the axes, that's good. But the one that I have to break down into components is this tension force from chain B, so I have to break that down into x and y components. I'm going to go ahead and do that up here. So I'm going to make a copy of that vector up here, and I know that that angle is 60 degrees, and I want to break it down into components along the x direction and the y direction, and those two components are going to form a right angle. So what I have here is a right triangle. Since I have a right triangle, I can use some trig to figure out what the length of each side is. So let's write down SOHCAHTOA. If I want to figure out what the opposite side is, I have to use, I know opposite, or I want to find the opposite side, I know the hypotenuse. That means the trig function I have to use a sine. So the opposite side is FTB times sine of 60 degrees. And now if I want to figure out what this component is, this is the adjacent side. So now I want to use adjacent and hypotenuse. Well, the trig function I need to use with those is cosine. So this side down here, its component at the bottom is FTB cosine of 60 degrees. Okay, let's replace this vector with its two components. So let's erase that vector and draw in this component, the x component, and let's draw in that component. You'll notice that I moved it along the axis, which is perfectly okay. That is a perfectly okay thing to do with vectors. As long as we keep their same magnitude and their same direction, they don't care where they're placed. Okay, now all of these vectors are along an axis of one or another, one sort of another, which means I can go on to step number 5, which is to write Newton's second law for the x direction and the y direction. Okay, I am going to erase this little chart here now that I'm done with it. And let's use that new space to write Newton's second law. And normally on a board or on a piece of paper, I tell you to write x and y side by side, but I don't have enough room to write these equations down and make them legible to you. So I'm going to start off with the x direction myself, and then I'll work with the y direction in a moment here. So in the x direction, I write F net equals ma. The F net for this particular the x direction is going to be these two vectors added up together. So I'm going to take FTB cosine of 60 degrees, and FTA is pointing in the opposite direction, so I need a negative sign there. This ball is not moving, it's not accelerating in any direction, so that means its acceleration is 0. So that's why there's 0 on the right hand side. I can do a little bit of simplifying here. I know that cosine of 60 degrees is 0.877. So I can rearrange this. Oops, I'm sorry, that's 0.5. Whoa, where was I thinking? This is 0.5 actually, not 0.877. So I have 0.5 times tension force in chain B minus tension force in chain A equals 0. Okay, without any further information, that's as far as I can get that one. So now let's turn our attention to the y direction. So now let's write Newton's second law for the y direction. Now I'm looking at forces only in the y direction. That means I have this force and that force, and I have to add those together. So now I have FTB sine of 60 degrees plus negative FG, since gravity is pointing down, the negative y direction. And again, we have no acceleration in the y direction, so I write 0 on the right hand side of the equation. Sine of 60 degrees is 0.877. So I can rearrange this, and I can write this as equal to m times g. So I have 0.877 times the tension force minus mg equals 0. I know the mass of the ball, that's 50 kilograms. I know that g is equal to 9.8. Again, I don't want to use negative 9.8 because negative 9.8 tells me 9.8 downward, but I've already told this equation that this force is pointing downward, so it already has the negative sign, which means I do not want to try to put it in again here. So this is just going to be 9.8. So I have 0.877 times the tension force minus 50 times 9.8 equals 0. Well, I can evaluate what this is, and it turns out to be 49. So, or 490, excuse me, not 49. And I could finish this off, but I'm going to do that in the next step. So the final step is to solve the system of equations. And just to show you I have a system of equations, let's actually take the last equation we had in each of the two directions. So in the x direction, we finished off with this equation right here. In the y direction, we finished off with this equation. I have two equations, two unknowns, but I notice that this equation over here has two unknowns. This equation only has one unknown. So probably the best way for me to solve this system of equations is by what's called substitution, which means I'm going to solve this equation for the tension force in chain B and then substitute that into this equation right here so that I can find the tension force in chain A. Well, let's go ahead and go forward with that plan. So I need to add 490 to both sides of the equation, so I get this. And then to get rid of the 0.877, I have to divide. So when I divide both sides, I will get this. So the tension force in chain B is just 490 divided by 0.877, and the number I come up with is 559 newtons. I can now use that over here to substitute in. Notice that I've replaced the tension in chain B with 559. I can evaluate that to come up with this equation, and then I want to get FTA by itself, which means I want to subtract 279 from both sides. I actually flipped that well, no, I didn't flip that equation around. So I get negative FTA equals negative 279, and multiply both sides by -1, and the tension force in chain A is 279 newtons. So that is how you solve a problem where you have no normal force. You're just going to use the most convenient coordinate system possible, and that usually means you want gravity pointing in the negative y direction. In the next video, I'm going to show you how to solve problems involving pulleys, and I look forward to seeing you then. Bye.